Hello, everyone. So today I want to talk about the topic of the derivatives and differentiation. So last time we finished the chapter for limits and continuity. So today, chapter 2, derivatives. So let's start with tangent lines and the derivative definition. So in high school, you learned about the secant lines, right? The lines that connect 2 points of a graph, the graph of a function, and how to find the slope of such a line. So let's consider the function. Let's say y equals f of x, and 2 points, let's say x1 and f of x1, and x2 and f of x2 on the graph of this function. Okay, so let's say we have a function here. And let's say this is, for example, x1, f of x1. And this is another point, let's say x2, f of x2. And this is the line connecting these 2 points. And this is y equals f of x, right? So this is called the secant line. Secant line means the line connecting 2 points of the function. So we have 2 points here, and we consider the line connecting those 2 points. Now, what is the slope of secant line? So you learned about the slope of a line in high school. So what is the slope of this line? The slope of this line, m equals y2 minus y1 over x2 minus x1. Now, what is y2 and y1? Well, you know that if you have a point on the graph, if let's say you have a point on the graph of a function f of x, if the x value, for example, is a, then the y value is f of a, right? So for example, if you have a point on the graph of y equals x squared, if x value is 2, y value has to be 2 squared, which is 4, and so on. So here we have points, the x values are x1 and x2, so the y values must be f of x1 and f of x2. So what is the slope? y2 minus y1 over x2 minus x1. So that's going to be f of x2 minus f of x1 divided by x2 minus x1. Right? So this is the slope of secant line. Now, how about if you want to have, so this is slope of, let's write down slope of secant line. What about if you want to consider tangent line? Now for tangent line is a tangent line, let's say tangent line is a line that just touches the graph of a function. Okay, so now the tangent line at x equals x1. So in the graph above, to obtain the tangent line at x equals x1, what can we do? So let's look at this graph. So this is secant line, the line connecting 2 points, x1 and f of x1 and x2 and f of x2. Now, what about if I want to look at the tangent line at x1, for example? Tangent line at x1 would be this line here. And how can I get this line? Now let's look. See if x2, if I choose x2 to be closer to x1. So right now x2 is a little bit far from x1. How about if I choose it a little bit closer to x1? What happens? So let me show you. See, for example, let's say x2, if x2 is here, for example. This is another choice for x2. Right? Now, if I consider the secant line between x2 f of x2 and x1 f of x1, I would get this line here, right? Which is very close to be the tangent line at x1. Now, if I let x2 to be even closer to x1, right? So let's say, for example, I delete this. I choose the x2, which is even closer. So for example, see here, very close to x1. So right now my x1 is here. And if I consider the tangent line between these 2 points, x2 f of x2 and x1 f of x1, what happens? The secant line between connecting these 2 points will be actually in practice will be the tangent line at x1. So the best way to define the tangent line at x1 is that I can start with the secant line between x2 f of x2 and x1 f of x1, but then I move x2 closer and closer to x1, which is the place where the concept of limit appears. So in the beginning of the semester, I promised you that the concepts in calculus, such as limits and derivatives and integration, will appear naturally everywhere in mathematics, physics, and engineering. So this is the one place where this concept appears. We want to look at the tangent line, and we want to know what is the best way to define the tangent line. But we already learned in high school to define secant lines, the lines connecting 2 points of the graph. So we defined that line, and then we decided to move x2, let x2 move closer and closer to x1. So as x2, which is right now in the beginning here, then we let it move closer and closer to x1. Then the secant line connecting these 2 points, x1 f of x1, x2 f of x2, becomes closer and closer to be a tangent line like this at x1. Okay, so to obtain this, we can consider the secant line connecting x1 f of x1 and x2 f of x2, and let x2 move towards x1. So m of the tangent line, the slope of tangent line at x equals x1 is equal to the limit f of x2 minus f of x1 divided by x2 minus x1 as x2 approaches to x1. Okay, so this is this. So we started with this expression for the secant line, then we decided to let x2 move closer and closer to x1, and that's how we got the slope of tangent line at x1. So this notion, or this concept or notion, is called the derivative at x equals x1, and is formally defined as follows. So definition, let y equals f of x be a function let y equals f of x be a function. We say that y equals f of x is differentiable is differentiable at x equals a if limit f of x minus f of a over x minus a as x approaches to a exists. And in this case, we denote the value of this limit by f prime of a. F prime of a called the derivative of f of x at x equals a. If the limit above does not exist, then we say that the function, y equals f of x is not differentiable at x equals a. Or we say that f prime of a does not exist. Okay, so derivative at the point means limit f of x minus f of a over x minus a, right? So f prime of a is defined as, in other words, let me say so. F prime of a is defined as limit f of x minus f of a over x minus a as x approaches to a. F prime of a is defined as this limit. So if this limit exists, we say that the function f is differentiable at x equals a, and the value of derivative at x equals a denoted by f prime of a is defined as the value of this limit. If this limit does not exist, and we know that infinity, if the limit is infinity, it's also considered as not exist, or if the left limit and right limit are not equal, for example, these are the cases where the limit would not exist. In those cases, we would say that the function f is not differentiable at x equals a, or we say that f prime of a does not exist. So the first remark I want to tell you here is that remark and this definition can be rewritten in the following form. So the definition above can be written, can be equivalently written as follows. F prime of A equals limit f of A plus H minus f of A over H as H approaches to 0. So how can we see the equivalency of this form, the original form, and this form? So in some books, this one is written as the original definition of derivative. Some books, this one written, but it can be easily shown that they are equivalent. So no matter whether you use this one as original definition or this one as original definition, you can use any of these form, whatever form that you find more convenient, you can use that form. So the proof, let's look at the proof for this remark. So proof, let's start with the this expression, f of x minus f of a over x minus a. So by definition, f prime of a is equal to limit f of x minus f of a over x minus a, x approaches to a. Now, how about if I use a substitution and I call x minus a as h? Then I'll have limit. So remember, I also said this before, that if you want to use substitution and change variable, then you have to rewrite your new limit in terms of your new variable. So every x has to be replaced by h. So we have limit x approaches to a, so x has to replace by h. So if x approaches to a, as x approaches to a, h, which is x minus a, will approach to 0. So h will approach to 0. And then we have f of x, which is a plus h, minus f of a over h. Right? So x is a plus h, and then we have minus f of a over h as h approaches to 0, which was the expression we wanted to show. All right. All right, let's look at an example now. Let f of x equals x squared plus 2x. Find f prime of 1 and f prime of a for an arbitrary real number a. So f prime of 1, for f prime of 1, how can we compute it? So f prime of 1 is equal to limit f of x minus f of 1 over x minus 1 as x approaches to 1. And then this is equal to limit f of x is x squared plus 2x. So x squared plus 2x minus 3 over x minus 1, x approaches to 1. And then this is equal to limit x plus 3 times x minus 1 over x minus 1, x approaches to 1. And then this is limit x plus 3, x approaches to 1, and then this is 1 plus 3, which is 4. Right? So we had, when we calculate the limit as x approaches to 1 of this function or this fraction, when you replace x with 1, 1 plus 2 is 3 minus 3 is 0. 1 minus 1 also 0. So we get 0 over 0, which is indeterminate. And you remember when we have an indeterminate form, like 0 over 0, we have to simplify. Now, if you have a polynomial over another polynomial, we can simplify by factorizing. Factorizing top and factorizing bottom. So we did that, x plus 3 times x minus 1 over x minus 1. And then we are left with x plus 3 as x approaches to 1, which gave us 4. Okay. So this is f of x is differentiable at x equals 1, and f prime of 1 is equal to 4. Now for the second part, for f prime of a, so for f prime of a, we could still use the first definition. See, we had two equivalent definitions. One of them was limit f of x minus f of a over x minus a, and one of them was limit f of a plus h minus f of a over h. Now you can use either of these two definitions, whatever you find more convenient. Now let's say if I use the second one, f of a plus h minus f of a over h, then what do I get? Then I'll get f prime of a equals limit f of a plus h minus f of a over h as h approaches to 0. And then this is limit a plus h the whole squared plus 2 times a plus h minus a squared minus 2a divided by h approaches to 0. And then this is limit a squared plus 2ah plus h squared plus 2a plus 2h minus a squared minus 2a divided by h approaches to 0. And then this one we get limit, so a squared cancels with a squared, 2a cancels with 2a. And then I'll be left with 2ah plus 2h divided by h approaches to 0. And then this is limit, so h I can take it out, 2a plus 2 divided by h. Now h cancels with h, and then I'm left with 2a plus 2. So we can say that if for any x equals a, with a belongs to R, f of x is differentiable at x equals a, and f prime of a is 2a plus 2. So at any point a, f of x is differentiable at a, and f prime of a is 2a plus 2. Okay. Now let's look at another example. Let f of x equals absolute value x. Determine whether f of x is differentiable at x equals 0. So how can I check whether f of x is differentiable at x equals 0? We need to look at, so solution, let's evaluate limit f of x minus f of 0 divided by x minus 0 as x approaches to 0. Then what do we get? So we get limit absolute value x minus f of 0, absolute value 0 is 0, divided by x minus 0, x approaches to 0. So now I can calculate the right limit and left limit. So right limit would be absolute value x over x, x approaches to 0 from right. And then this is limit x over x, right? So x approaches to 0 from right means x is bigger than 0. So if x is bigger than 0, absolute value x will be equal to x itself. And then I'll get limit x over x as x approaches to 0 from right. And then this is limit 1. X approaches to 0 from right, which is 1. And the left limit, absolute value x over x, x approaches to 0 from left. So if x approaches to 0 from left means x is less than 0. X less than 0 means absolute value x will be equal to minus x. So then we get limit x approaches to 0 from left minus x over x, and that's minus 1. So we can conclude that the right limit and left limit are not the same. And this means that limit, this means that f of x equals absolute value x is not differentiable at x equals 0. Because the limit that we said, limit f of x minus f of a over x minus a as x approaches to a, does not exist when a is equal to 0. So that means f of x is not differentiable at this point. Or in other words, we could say that, i.e., f prime of 0 does not exist. So this is another way to say that f of x is not differentiable at this point. And so as an exercise, you can show that. So if a is not equal to 0, show that f of x equals absolute value x is differentiable at x equals a, and find the value of f prime of a. So differentiability, of course, like continuity. Continuity, remember, depends on the function and depends on the value of a. So similarly, differentiability depends, of course, on the function and also on the value of a. So absolute value x is not differentiable at a equals 0, but it's differentiable at every other point, right? So only at, so this is the basically graph of absolute value x, and we justify that derivative at the point represents the slope of tangent line at that point. So at 0 from right, the tangent line has slope 1. From left, the tangent line has slope -1. And our calculation also verified this. So right slope and left slope were not equal, so we can say slope does not exist overall, or the function is not differentiable at a equals 0. But if a is positive, so the answer will be f prime of a will be equal to 1 if a is positive, and f prime of a will be -1 if a is negative. See, if the value of a is positive, if you are here, the slope of tangent line will be 1, and if you are here, the slope of tangent line will be -1. Okay. So this is an example of a function which is not differentiable at a point. So you see this function is still continuous at a equals 0. We previously saw that this function is continuous at a equals 0. First of all, because there is no hole or break intuitively, and the formal justification is that because the right limit and left limit are equal at a equals 0 for the function itself. See? Please note here that for right limit and left limit of this expression for the function were different. But right limit and left limit of the function itself at a equals 0 are equal. So see, let me even give a remark here. Although the function above is not differentiable at equals 0, but it is continuous at this point. Since limit f of x as x approaches to 0 from right means limit absolute value x approaches to 0 from right equals limit x as x approaches to 0 from right, and that's 0, and left limit is also 0 because this is limit minus x as x approaches to 0 from left, and that's minus 0, which is also 0. So we can say that left limit and right limit are equal, and they're equal to 0. So that means the whole limit is equal to 0, which is same as the f of 0. So, and this means f of x is continuous at x equals 0. So we previously saw that if the limit exists and is equal to f of a, then we can say that the function is continuous at that point. So here, limit f of x exists and is equal to f of a. Limit f of x as x approaches to 0 exists and is equal to f of 0, which is 0. So f of x is continuous at this point. So f of x is continuous, but still not differentiable because yes, limit f of x exists, but limit f of x minus f of 0 over x minus 0 does not exist. So limit f of x exists and is equal to f of 0 means the function is continuous. Limit f of x minus f of 0 over x minus 0 does not exist means the function is not differentiable. So the conclusion is like this. So conclusion, if a function is continuous, then it may or may not be differentiable. If it's continuous, we cannot say it's differentiable or not differentiable. Depends on the example. This function absolute value x is continuous but not differentiable. But previous example, for example, this one, which was a polynomial x squared plus 2x. So this function was continuous and also differentiable. So if a function is continuous, we cannot be sure. It could be differentiable like this example, or it may not be differentiable like this example here. So we can't say for sure whether the function is differentiable or not if we just know about the continuity. But another question we could ask here is, what about if we know that the function is discontinuous? So question here, if a function is discontinuous, if f of x is discontinuous at x equals 0, can we conclude that f of x is, or x equals a, let's say in general, can we conclude that f of x is not differentiable at x equals a? If it's continuous, then we cannot be sure. But what about if it's discontinuous? Then can we say for sure it's not differentiable? The answer is yes. If a function is discontinuous, then we can say that it is not differentiable. If a function is discontinuous, then it cannot be differentiable. So proof. So what do we want to show? We want to show that if f of x is discontinuous at x equals a, then f of x is not differentiable at x equals a. So to do this, to prove this statement, to prove this, we use proof by contradiction. Proof by contradiction. So in proof by contradiction, we assume what we want to show is wrong. We want to show that f is not differentiable. So if this is wrong, that means f is differentiable, right? So suppose that f of x is differentiable at x equals a, right? So for example, proof by contradiction, let's say you want to show that root 2 is irrational. If you want to use proof by contradiction, you want to show root 2 is not rational, but you have to assume that root 2 is rational and then reach a contradiction. So same thing here. We want to show that f is not differentiable at x equals a. So let's assume this is not true. Then that means f is differentiable at x equals a. And we want to reach a contradiction. The contradiction, as we will see, it will be the fact that f of x is continuous at x equals a. This will be a contradiction because contradiction means something impossible. But of course, because I'm assuming f is discontinuous at x equals a, so if I can conclude that f is continuous at x equals a, that will be impossible. That will be considered as impossible because it's not possible that f is continuous and discontinuous at the same time, right? So that will be my contradiction. Let's see how we can reach that contradiction. Suppose that f of x is differentiable at x equals a. Then what can I conclude? When can I say that f is differentiable at x equals a? So I always say in all my math courses that you have to always look at the definitions over and over. What does definition tell you? Well, you're assuming that f is differentiable at x equals a. So what does definition tell you? If f is differentiable, then we can say that which limit exists. See? When can we say that the function is differentiable here? Let this, we say that f of x is differentiable at x equals a if this limit exists. And in this case, we denote the value by f prime of a. So now, right now, I'm assuming that f of x is differentiable at x equals a. So that means by definition, this limit here, I can say that it exists and the value is f prime of a. So then by definition of differentiability, limit f of x minus f of a over x minus a as x approaches to a exists, and its value is f prime of a. So f prime of a is equal to limit f of x minus f of a over x minus a, x approaches to a. Now I want you to note that f of x minus f of a is equal to f of x minus f of a over x minus a times x minus a, right? Which is true for this equality is true for x not equal to a. So I have an equality here, f of x minus f of a equals this expression times this expression, right? Now, limit of this expression exists. Why? Because of my assumption. My assumption says that this limit exists and its value is f prime of a. So limit of this expression exists and is equal to f prime of a. What about limit of this expression as x approaches to a? Limit of this expression also exists and is equal to 0, because it's just a linear function, a simple polynomial. If x approaches to a, limit will be a minus a, which is 0. So now, then limit f of x minus f of a over x minus a as x approaches to a is equal to f prime of a, and a limit x minus a as x approaches to a is equal to 0. So what can we conclude? We can say that a limit f of x minus f of a as x approaches to a exists, and its value is f prime of a times 0, which is 0. So this is by limit properties, right? Limit properties. Limit properties tell us that if you have two functions multiplied by each other, limit of first one exists, limit of second one exists, then limit of multiplication or product of them also exists and is equal to limit of the first one times limit of the second one. Right? So this limit of f of x minus f of a exists, and its value is limit of first one, which is f prime of a, times limit of second one, which is 0. Now I want to show that limit f of x itself exists. So next I want you to note that f of x can be written as f of x minus f of a plus f of a. Right? Of course, f of x can be written as this form by just adding and subtracting f of a. Now, this part I already showed that the limit exists and is equal to 0. This part is a constant function, so its limit exists and is equal to the same value, which is f of a. Now, limit f of x minus f of a as x approaches to a exists and is 0. See above. And limit f of a as x approaches to a exists and is f of a. So what can we conclude? We can conclude that limit f of x approaches to a exists and is how much? 0 plus f of a, which is f of a. The first part, limit is 0, then we have f of a, so the limit of addition of two functions, if each part the limit exists, the limit of addition is addition of limits. So the first part has limit 0, the second part limit f of a, so the addition will be 0 plus f of a, which is f of a. Or we can say, and its value is, well, this means f of x is continuous at x equals a, and this is a contradiction with f of x being discontinuous at x equals a, which was given as an assumption. So if limit of the function exists, limit of f of x exists and is equal to f of a, by definition of continuity, this exactly means the function is continuous. The function is continuous if limit f of x exists and f of a is defined, and the value of the limit and f of a are equal, which is the case here. So the function is continuous, but my assumption was f of x is discontinuous at x equals a. So this is a contradiction, which means something impossible. It's impossible that f of x is continuous at x equals a and also discontinuous at the same time. It's not possible. Okay, so this contradiction means that, therefore, f of x is not differentiable at x equals a as desired. Remember, our original question was, if f of x is discontinuous at a, can we conclude f of x is not differentiable at a? The answer is yes. And we said we are doing proof by contradiction. So we assume f of x is differentiable at x equals a, and we reach a contradiction, which we did that. So this means that we prove this, that if f is discontinuous, then f of x cannot be differentiable. F of x must be non-differentiable at the point if the function is discontinuous. So for example, we can look at this function. Let's say consider f of x equals 2x plus 1 if x is bigger than or equal to 2, and 3x if x less than 2. Is f of x differentiable at x equals 2? So the answer is no. Why no? Since limit f of x as x approaches to 2 from right is how much? Is limit 2x plus 1 as x approaches to 2 from right. And this is 2 times 2 plus 1, which is 5. And the left limit at 2 is limit. So if x is less than, left limit means x is less than 2. If x is less than 2, the formula will be 3x. And then this will be 3 times 2, which is 6. So since the right limit is 5, left limit is 6, we can say that we can conclude that limit f of x as x approaches to 2 does not exist, right? If the left limit and right limit are different, that means the whole limit does not exist. And if the whole limit does not exist, means f of x is discontinuous at x equals 2. And this means f of x is not differentiable at x equals 2. See the property above. Right, we just showed that if a function is discontinuous, then it has to be non-differentiable. Then f of x will be non-differentiable at that point. Okay, now let me add part B. So let's say this was part A. And for part B, is f of x differentiable at, let's say, x equals 4. So at x equals 4, at x equals 2 function was discontinuous, therefore non-differentiable. At x equals 4, the function is continuous. So can we say it this way? Can we say that limit f of x as x approaches to 4, if x is around 4, I have to use which formula? I have to use the formula for x bigger than 2, which is 2x plus 1. As x approaches to 4, and then this is 9. And therefore this means, which is same as f of 4, right? And that means f of x is continuous at x equals 4. And that means f of x is differentiable at x equals 4. At 4, the formula is 2x plus 1. So limit exists and is equal to 9, which is same as f of 4. If limit, the value of the limit is same as value of f of 4, that means the function is continuous. And if it's continuous, then it has to be differentiable. So is this reasoning correct? This reasoning is wrong. Why? Which part do you think is wrong? Which step is wrong? The last step is wrong. Up to here is correct. Yes, because of this reasoning, the function is continuous. But if a function is continuous, we cannot conclude that it has to be differentiable. See? Here we said, if a function is continuous, then it may or may not be differentiable. So if a function is continuous, we cannot conclude that it has to be differentiable. And I gave you the example already, right? So absolute value x besides continuous at 0, but not differentiable at that point. So from continuity, we cannot conclude differentiability. So wrong, because if a function is continuous, it may not be differentiable. See above. So this is the wrong reasoning. What is the correct reasoning? So correct solution. To show a function is differentiable, we have to look at the definition of differentiability. Definition of differentiability is you have to look at the limit the limit f of x minus f of a over x minus a as x approaches to a. So let's look at that limit, the correct solution. Let's look at limit f of x minus f of a over x minus a, and a here is 4. F of x minus f of 4 over x minus 4 as x approaches to 4. So then this is limit 2x plus 1 minus f of 4 is 9 over x minus 4, x approaches to 4, right? If x is around, if x is very close to 4, means x is bigger than 2. And for x bigger than 2, the formula for the function is 2x plus 1. Then this is limit 2x minus 8 over x minus 4, x approaches to 4. And then this is, I can take 2 out over x minus 4, x approaches to 4. And then this is x minus 4 cancels, so the answer is 2. So we can conclude that limit f of x minus f of 4 over x minus 4, x approaches to 4 exists, and its value is 2. So this means f of x is differentiable, right? Is differentiable at x equals 2, and f prime of at x equals 4, sorry, at x equals 4, and f prime of 4 is equal to 2, right? So definition of differentiability says if this limit exists, then we call the function as differentiable at this point. The point is 4 here. So at x equals 4, the function is differentiable, and f prime of 4 is defined as the value of this limit. So now here in this example, the value of this limit is 2. So that means f prime of 4 is 2. So this is the correct solution for showing that f is differentiable at that point. So please be careful. If you conclude differentiability from continuity, that will be considered as a wrong solution, and you will not get any points in the exam. So this is the way that you have to show that the function is differentiable. But if you want to show that the function is not differentiable, if from discontinuity you conclude not differentiability, then that is correct. Okay, so sometimes I give the example as because sometimes it's confusing for some students. So I say, for example, if it's a Monday, then for example, let's say I come to the college. This is not same as saying that if it's not a Monday, then I will not come to the college, right? These are not the same statement. One of them could be true, one of them could be wrong. So for example, if it's a college, if it's Monday, then I come to college. This may be true, but at the same time, it may be true that if it's not a Monday, I still come to the college. Because for example, let's say I come to college on Monday and Thursday. So if it's a Monday, I come to college, but if it's not a Monday, I cannot conclude I do not come to the college. Maybe it's a Thursday and I still come to the college, right? So in logic and in mathematics, P implies Q is not equivalent with not P implies not Q. So in this case, not continuous implies not differentiability. But at the same time, continuity does not imply differentiability. Okay, guys.